Assalamualaikum warahmatullahi wabarakatuh and good day. So my name is Shazza Aziz bin Noordin. My matrix number is 183861. So I would like to present my FYP entitled Experimental Investigation and Mathematical Modeling of Pluronic F127 Dissolution. My supervisor is Dr. Faizal binti Muhammad Yassin. Okay, now let us proceed to the keywords for this study. So there are 4 keywords. The first one is Pluronic. The second one is dissolution. The third one is myself. And the last one is mathematical model. Okay, next we proceed to the introduction for this study. So, Pluronic are non-ionic tri-block copolymer composed a central hydrophobic chain of polyoxypropylene PPO flanked by 2 hydrophilic chains of polyoxyethylene PEO. So we are going to focus on the methylation of F127, particularly as it relates to the pharmaceutical application, which used in drug carrier applications. Okay, let's now move on to the literature review. So, according to Johann Jin 2011, Pluronic F127 is a ambiphilic block copolymer ABC, whereby the ambiphilic characteristic shows that it possesses both of hydrophilic and hydrophobic character, which this compound show good affinity for both water and oil. So it's usually used in delivery of therapeutic agent result from their unique chemical compositions, according to ML Adam etc. 2003. According to Kyuga etc. 2011, due to the ambiphilic characteristic of the pluronic, they can aggregate to form self-assembled micelle structure when being put above the critical micelle concentration, say MC, when placed into a aqueous solvent. The self-assembled structure has been applied in drug delivery system and engine delivery. Okay, let's now proceed to the problem statement for this study. The size distribution and also the dissolution rate of F127 is very crucial for making F127 as a very efficient drug carrier, and furthermore it's very convenient if we could predict the methylation size of F127 based on the parameter that affecting the dissolution rate. Therefore, in this study we are going to identify the factor that affecting the methylation size and also the dissolution rate of F127, and later developing the mathematical model on the methylation size of F127. Now let us continue with the research objective. The main objective is to resolve the F127 and obtain a mathematical modeling on the methylation size of Pluronic F127, and then it's later divided into 3 more sub-objectives to fulfill the main objective of this study. Okay, now we proceed with the significance of the study. So there will be 3. The first one is to study the factor of dissolution rate, to study the factor that affect the size of my cell, and the last one is the mathematical modeling on the size of my cells. Okay, let us now proceed with the methodology. So as you can see on the left side is the apparatus setup for the dissolution. So this is the flow diagram for the experiment to take place, and also at the bottom is the material and apparatus used for the experiment. Okay, now continuing with the methodology. So we are going to manipulate the parameters that affecting both dissolution rate and also methylation size of Pluronic F127. There are 4 parameters that need to be considered. The first one is temperature, pH, stirring speed, and protein concentration. As for protein concentration, we are using BSA, bovine serum albumin. Okay, now let us proceed with the analysis. So the first analysis is DLS or nanosizer. So this analysis purpose is to identify the size of F127 micelle form. So as we could see, the peak is indicate the most size distribution of the micelle particle. Moving to the next analysis, which is the zeta potential. So the significance of zeta potential is to show the stability of the micelle form. So this test only done for the sample with the presence of the protein. Okay, now we're going to proceed with the final analysis, which is the FISEM. So FISEM was used to examine the morphological structure of F127 micelles. So the imaging was carried out at accelerating voltage of 10 kV and with magnification of 25,000, 50,000 and 100,000. Okay, now we're going to proceed with the result and discussion. So the outcome will be 3, dissolution rate of F127, micelle size of F127, and the last one is mathematical model. Okay, now we are going to proceed with the result and discussion on the dissolution rate of F127. So this is the data. Okay, now we're going to jump into the temperature effect on the dissolution rate. So with the increase of temperature, it gives lesser time for it to dissolve. It's because increase of temperature gives rise to the higher CMT required by F127. The standard free energy of micelle formation decreases monotonically with increasing temperature, thus giving a positive standard entropy of micelle formation and indicating the hydrophobic effect in the micelle formation. Next, we are going to continue with the stirring effect on the dissolution rate. So the dissolution rate increases with the increment of stirring speed. More surface area of substance is exposed to the solvent as the stirring takes place. The higher the surface area in relation to the volume is, the faster a solid will dissolve. Next, we are going to proceed with the pH effect on the dissolution rate. So there were no specific trend observed. However, slightly acidic or basic condition give better dissolution rate compared to the neutral pH condition. So now we are going to proceed with the last parameter, which is the protein concentration effects. So as we could see, as the protein concentration increase, it requires more time, as F127 require more time to load the protein within its micelle as the higher protein concentration was used. Okay, next we are going to discuss on the F127 micelle size form. So this is the data obtained from the analysis of DLS. So we're going to jump straight into the first parameter, which is temperature effects. It shows that with the increase of temperature, shows the increase of size. As block copolymer solution temperature rise, the PPO block is gradually losing its hydrogen sphere, leading to greater interaction between PPO blocks. On the other hand, the PEO blocks retain their strong interaction with the water. Thus, it's common for all amphiphilic molecules. The differentiating phase preference of the blocks drive the copolymer to form bigger micelles. Okay, now we're going to jump into the second parameter, which is the pH effect. As we could see, the size of micelle increased slowly for pH 3, 5, and 7. However, it's drastically increased when it hits the alkalinity conditions. The enlargement is due to the ionization on the micelle, causing it to bloat, and thus the micelle rapidly grows in size. So for the stirring speed effects, it shows no change in size with the lowest and the highest speed. This due to the lack of presence of temperature and also concentration, which is the main element in micelle formation size. So as for protein, we could see that the size is enormously large, whereby it's in micron size. This due to the protein used, which is BSA. BSA is already a large protein particle, making it incorporated into the F127, making the F127 micelle to be bigger. So this is the mathematical model of F127 micelle size. So we only incorporated two parameters, which is pH and temperature. The model was generated by ANOVA using the design expert software, and the predicted size is in nanometer scales. To validate the equation, we run another test, and this is the results. The limitation for this equation is that the sample should be in range of 25 degrees C to 45 degrees C. Meanwhile, for the pH, it needs to remain in pH 3 up to pH 11 for prediction to be very accurate. So, as conclusion, the goal of this study has been accomplished. The 4 parameters play a very important role in the dissolution process. However, for the micelle size, it is found only temperature and pH were the main factor. And as for the mathematical model, it is obtained and show a very promising usage in the future. As for recommendation, it is recommended to add more parameters and also to add more range to the manipulating parameters. I think that's all from me. Thank you.